Hello and welcome. This is our fourth step in journey of deep learning. We learn about introduction of neural network and concepts of deep learning in previous lectures. We also learn about forward propagation and implemented forward propagation using Python in our previous lectures. From this lecture, we will start our journey in direction to learn about backward propagation. But first of all, let us understand the concept of gradient descent. Gradient descent problem I have already broadly discussed in my previous machine learning lecture series. But again here, I will cover it briefly as we need to refresh the concept in process to understand the backward propagation and vanishing gradient problem. So let us start our journey. Now, in this particular video lecture, we will learn about gradient descent and understand its need to know about backward propagation. We will go through four aspects related to the backward propagation step by step in these and coming lectures. First objective is to understand what is gradient descent algorithm and its concepts. Second objective that we will cover will be related what back propagation is and how neural network learn and update their weights and biases. A third aspect which we will cover will be the concept of vanishing gradient problem. And finally, we will cover the activation function. Let us understand the gradient descent algorithm first. To understand gradient descent, we revisit the concept of cost function. Consider we have a scatter plot which represents some data points with respect to axis z and x. Here we have data points we generated which is having real relationship as z is twice to x, that means z equal to 2x. So, in general form, we can say that the relationship here z equal to wx, where w is the weight, and in our particular case, w is 2 right now, as you can see in the figure. Hence, we can say that we loss or cost function is sum square of actual value of size of z minus predicted value of z using z equal to wx, which is divided by 1 by 2m, where m is total data points. Actually, if you notice, it is nothing but mean square error. So basically, we are concerned with the loss or the cost function. So we represent it as a JW. Hence, we can say that the cost and loss function JW is sum square of actual minus predicted value divided by 2m. Our aim is to minimize the cost or loss function JW. Consider this example for our previous function z equal to wx, where w equal to 2. We have plot a graph which represents cost function jw against the w. We can observe the parabolic representation where we obtain minimum cost jw when w equal to 2 for our example. This is called global minima. Basically, our motive is to establish a relationship between given x and predicted z in such a way that cost or loss function is optimized. And for this purpose, we need to choose the w such that we obtain our target. So, we want to optimize the value of w. How to optimize it? Well, to optimize the W, what we use is algorithm known as gradient descent. Let us understand what is gradient descent. Gradient descent is an iterative optimization algorithm for finding the minimum of function. Let us understand how the algorithm works. We take some random value for w. For this example, let us take the random value as w equal to 0.2. This will be our start value. Now, with every iteration, we will take a step towards the global minimum value, and the step will be determined as learning rate. The learning rate will be a step value that will lead to the next value of the w. Suppose we call the start value as W0, then the next step we will obtain after adding the learning rate as dj derivation of j with respect to w, that is dj by the dw. It is derivation of cost function and we call it as w1. Since step value is negative, hence actually the obtained w1 will be w0 minus the step value. Similarly, the iteration will take place until we meet the minimum of the cost value jw or close to the jw. Here, we need to understand that if the step value is very high, then it is possible that the value w will cross the global minimum, and if the step value is too small, number of iteration will increase and it will slow down the algorithm. Hence, it is necessary to choose the step value appropriately. Take an example. If we keep our learning rate as 0.4, then we obtain for initial iteration where w equal to 0, we obtain just a horizontal line for relation of z equal to wx. Now for second iteration, the step will move towards the minimum w. This relationship is shown in form of green line. Now its second iteration, again we add the step value and we can see that it is more closer to the global minimum W. This relationship can be seen as pink line. With every iteration, we come close to the global minimum cost function JW. This can be seen in our graph representing relationship between Z and X. With every iteration, we come close to the global minimum. Wi trends to Wi minus learning rate multiplied by derivation of cost value with respect to W. This is how the global minimum of cost function is achieved using gradient descent algorithm. Now that we understand how to optimize a parameter that function depends on, we are now ready to start learning about back propagation and how neural networks learn and optimize their weight and biases. In coming part of the lecture, we will understand the concept of backpropagation and then about vanishing gradient problem. Hope you are clear with the concept of gradient descent problem by now. Thanks for being with me in this lecture. Learn, share and grow. Have a great day. Thank you.